Every sound is produced by a vibration. Vibration is the back and forth movement of an object. We can hear only when the sound energy reaches our ears. So how does it travel?
Sound travels in the form of sound waves.
And there are two types of waves, the transverse waves and the longitudinal wave.
In transverse waves, the particles vibrate at a right angle to the direction of the wave. In longitudinal waves, the coils crowd closer together and move farther apart. This is because the vibrations are parallel to the direction of the wave.
Sound waves are longitudinal waves.
These waves travel in different speeds at different mediums, through solid, liquid, or gas. The vibration of particles produces waves. What are the parts of the wave? Wavelength. It is the distance between two consecutive compressions. Frequency. It is the number of waves passing through a point in a second, and it is measured in hertz. Period. It is the time required to complete one cycle. Amplitude. It is the maximum excursion of a particle of the medium from the particle's undisturbed position. The formula for the speed of the wave is the velocity is equal to the wavelength in meters over the period in seconds, or frequency in hertz multiplied by the wavelength in meters.
The yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 5.89 times 10 raised to negative 7 meters. What is the frequency of this radiation? We can find the frequency using the formula lambda is equal to V over F. The value of F is equal to 3 times 10 raised to 8 meters per second, which is the speed of light divided by 5.89 times 10 raised to negative 7 meters. The frequency is equal to 5.09 times 10 raised to 14 hertz. For waves on a string, the calculation for its speed is the square root of tension divided by the linear density. A particular guitar string has a mass of 3.0 grams and a length of 0.75 meters, with a tension of 1440 newtons. Find the speed of the waves on the string. The formula for this is V equals to the square root of the tension divided by the linear density, where the tension is equal to 1440 newtons divided by 3.0 times 10 raised to negative 3 kilograms over 0.75 meters, which is equal to 600 meters per second. As said earlier, sound travels in different mediums and they also travel at different speeds. For the ideal gas, velocity is equal to the square root of gamma times the constant 1.38 times 10 raised to negative 23 joules per Kelvin times the temperature over the mass. For liquids, velocity is equal to the square root of bulk modulus over the mass density. And for solid bars, velocity is equal to the square root of Young's modulus over the mass density.
Sound intensity. This is the power that passes perpendicularly through a surface divided by the area of the surface. Power is the amount of energy transported per second on the wave.
A man talks on the phone with the power of 0.5 times 10 raised to negative 4 watts. What will be his sound intensity at a distance of 5 meters?
Intensity is equal to power over area. I is equal to 0.5 times 10 raised to negative 4 watts over 5 meters. So the sound intensity is equal to 1 times 10 to the negative 5 watts per meter squared.
Decibel. The decibel is a measurement unit used when comparing two sound intensities. A factory machine produces a sound with an intensity of 2.0 times 10 raised to negative 3 watts per meter squared. What would be the decibel rating if 5 of these machines occupied the same room?
I is equal to 2 times 10 to the negative 3 times 5, which is equal to 1 times 10 raised to 2. To get the decibel, you multiply I over I naught to 10 decibel log. So, 10 decibel log times 1 times 10 raised to 2 watts per meter squared all over 1 times 10 to the negative 12 watts per meter squared, which would equal to 100 decibels.
The Doppler effect is a change in frequency or pitch of the sound detected by an observer because the sound source and the observer have different velocities with respect to the medium of sound propagation. For a moving observer and a stationary source, if the observer is moving towards the source, Fo is equal to Fs quantity 1 plus V naught over V. If the observer is moving away from the source, Fo is equal to Fs quantity 1 minus V naught over V. For a moving source and a stationary observer, if the source is moving towards the observer, Fo is equal to Fs quantity 1 divided by 1 minus Vs over V. If the source is moving away from the observer, Fo is equal to Fs 1 divided by 1 plus Vs over V. A fixed source emits sound of frequency 1000 Hz. What is the frequency as heard by observer A at rest, B moving towards the source at a constant speed of 20 meters per second, and C moving away from the source at the same time?
At rest. When both the source and the observer are at rest, apparent frequency is same as the true frequency. Therefore, frequency as heard by the listener at rest is equal to 1000 Hz. The velocity of sound in air is equal to 343 meters per second. The true frequency is equal to 1000 Hz, and the velocity of the observer is equal to 20 meters per second. To get the frequency of the observer, frequency of the source is multiplied by 1 plus the velocity of the observer over the velocity. So, 1000 Hz is multiplied by 1 plus 20 meters per second over 343 meters per second. The frequency of the observer is 1058 Hz. The frequency of sound in air is equal to 343 meters per second. The true frequency is equal to 1000 Hz, and the velocity of the observer is equal to 20 meters per second. The frequency of the source is multiplied by 1 minus velocity of observer over the velocity of sound. So, 1000 Hz is multiplied by 1 minus 20 meters per second over 343 meters per second. So, the frequency of the observer is 1000 Hz.